start the recording.
Yes, okay. So, welcome to everybody. We are here at point P5 CMS experience at Cern, and we are going to visit virtually, but it will be very exciting and interesting, this visit, the experiment, the detector. And I'm Sonia. I'm a particle physicist. I work at Cern in a different experiment, but I have the help here. So I wait here to welcome you also because I'm part of the communication service. But I have here Laza, who will be our guide underground. So I will
I'm also a particle physicist.
Yes.
I'm also but I do work on CMS since the very first days. I work for technical coordination, and I remember this experiment from the days when we had to walk through the mud on the bottom of the shaft. So yes, I have a pretty good idea.
So
of interesting things
we
to
will
show you.
profit of your knowledge and also all the information you have collected in these years, and I can feel what Laza is saying, because it's the same for me concerning the AMS experiment, which is now currently on the space station. And I really remembered how we built this experiment and how we had to fight to build this experiment, but we are very happy now that it's working exactly as CMS now very well. Now, first of all, I would like to ask.
May I interrupt you, Sonia?
Yes.
Because this is not just a simple virtual visit. This is part of the enrollment process as well. So we have another host, Erwin, who would like to say a couple of words.
Yes, okay, yes, Erwin.
Yes, good afternoon, everyone. First of all, I'm very happy that we could organize this visit, which has been specially designed for people who joined Cern over the last months and who, due to COVID, have not been able to visit any of the Cern installations. And I'm very glad that the CMS visit team has reacted so quickly, and that we could still organize this visit before Christmas. So there will be more visits coming after Christmas. Let's already enjoy this one. And I would like to thank again the whole CMS team for setting this up in such a short notice. Thank you.
Thank you to you, Erwin. And as Zoltan was talking before you, I would like also to ask Zoltan to introduce himself, and he will be co-speakers with me, as Laza also will do in the following. So Zoltan, do you want to say something?
Yes, thank you, Sonia. Today I'm not able to send image, therefore I'm just going to be a distant voice. I'm Zoltan. I'm working for the CMS experiment, the TC team, as well as the muons. Together with Noemi, she is somewhere slipping out from the picture, but together with her, we are, yes, exactly. Noemi.
She's busy, but okay, I can try to
exactly.
show her. Yes.
Yes,
she's there.
So I act today
mobile.
as your line director. I will be responsible for technical things, and as well as Noemi is doing that for the local mobile camera team. If it was a Hungarian virtual visit, we would be the guides as well. But this time we are in a lucky situation that we have excellent guides. So very probably we will stay silent unless Sonia will call me.
Zoltan, I will profit too to talk with you and to call you for sure. So you will be not quiet even today. So yes, of course. So I saw one question. So I would like to, as was already said, to ask questions in the Q&A chat, and I will try to answer depending on the situation and the description of the visit. So now I think we could start. Noemi she's still setting up all the devices so they can go underground. Are you leaving now? You want to start to go down, and I will start a small description. Is it okay?
I can start the share for you.
Yes, if you want, we can start
And
the
then-
share, and I will start now. I know that the audience is different kind of background. So we have scientific people, we have non-scientific people, and as far as I know, we have also students. So students and children. So I will try to make a balance, and I will profit of the experience, the huge experience of Laza, to give you all the technical details when you are on the ground, when you show us all the objects. So as you see on the screen, we have a picture of this area. You can see on this laptop. Sorry. Okay, yes, I can go. Okay, on the sorry, I have to move on to laptops. Okay, you can see on the if you see the picture on the top on the left, you see the Lemon Lake, and then you see many houses. The Mont Blanc is just in the middle, top middle, and this huge ring is the LHC accelerator. Its huge ring is 27 kilometers long, which is the double length of the Mont Blanc tunnel. If any of you were already passing through the Mont Blanc tunnel. On this accelerator, this is a tunnel which was built at minus 100 meters, so is underground. And this is not because it's dangerous. Let's say, of course, if you enter in an experiment cavern, usually you cannot do this because it's not allowed. But mostly this was because you see the area is very populated, and so the reason why we had to go down was also to find a stable layer where we could really build and put our experiences. Consider that you will see this detector, CMS. I think you get a virtual visit, but this virtual visit can makes you able to see much more as if you are coming in person. Of course, let's say the feeling is not the same, but what you can see today, it's really special. And these detectors, you will see they are huge, but they are assembled with a very, very high precision. These are the precision is 1 million sorry, because okay, the picture is changing. So the precision is at the level of microns. Let's say 1 micron is 1 million smaller than a micron, than a meter, and so this means that really you need a very high stability. Otherwise, all these parts cannot give you the good precision for our measurements, for the measurements. This is why we needed a stable layer, and this stable layer was found let's say more or less at minus 100 meter underground. Is a kind of rock we have here. It's called molar, if I'm not wrong. And this was built this tunnel, and then inside we put all the parts of the accelerator. And then as a person is riding a horse, we built in special points, as you can see here. Let me see if I can move the picture. Sorry, because I had to do many things. Okay, you can see on this picture again. You see this. This is the accelerator. Is not a real picture, but you see these points, specific points, where you see also these names: Atlas, CMS, where I'm here now, and the Alice on the left side, and the LHCb on the right side. Now, to give you the idea of the location, Atlas is behind the globe. So you can see is where we have the reception of Cern. Alice, if you are living, and I guess you are living in this area, is in Saint-Genis, more or less. So is already in France, because Atlas is in Switzerland. Then we have the border. I hope you can follow my mouse. Is in the border on the left. And then you have Alice in France, in Saint-Genis. And then you have LHCb is in France, but it's really close to the border. So we can say it's more or less close to the airport. And CMS, which is the farthest from the reception, it takes going by car. It takes more or less 30 minutes to go from the Cern reception to reach this site. And these points, so all the ring is located at -100 meters underground. And in these yellow points, you have the experiments. As you see, I profit to say that this picture gives me also the chance to talk a little bit more about the accelerator system, because usually we are able to, we talk about the accelerator and we talk immediately of the LHC, the last step of the accelerator chain. But as you see, the complex is much more complicated, is much more elaborated, and where everything starts, where you inject the particles, I will try to show you with the mouse, is where you see LINAC, the label LINAC 2 is in this place. So if you follow my mouse, you inject particles, and we will see which kind of particles they are. You inject particles in the LINAC 2. You reach the first ring. You start to, how to say, to work on this particle to make them being a good beam of particle, and particularly arranged in such a way you can do the what we call the bunch crossing and then the collisions. And then you go to the first important ring. The booster is important, but okay, much more important is the PS. PS stays for proton synchrotron, is an accelerator which was built, I would say the first ring built at Cern was built in 1959, still working. And as you see, if the PS is not working, nothing can happen in the LHC because the chain continues. If you follow my mouse from the PS we have here, you follow, and then apart other application you can do, you reach what we call another ring, which is a middle ring. This ring is the SPS. SPS stands for super proton synchrotron. It was built in 1966, and it was built as not as an accelerator, but not only, but also as a collider, which means that it was built in such a way that you had the two beams going inside, one on one direction and one on the opposite direction, okay? And there were two experiences, two detectors on this collider at that time, called the UA1 and UA2. UA stays for underground area 1 and underground area 2. And why I'm talking about this? Because this is an important part of the story, an important piece of the story of Cern, because in 1983, we announced the discovery of new particles, the W minus, W plus, and Z0 particles, which were confirming a part of the model we continue to build to describe our universe and the particle physics. So it was very important. As a consequence, the spokesperson of one of these two experiences, UA1, was awarded of the Nobel Prize in 1983. And is Carlo Rubbia, the physicist, the Italian physicist Carlo Rubbia, who then later became the Director General at Cern. After this, we we changed again the SPS. It became an accelerator, a pure accelerator, so only one beam circulating inside. And then we started to build the last ring you can see, where now we have the LHC. But when we built this last ring of 27 kilometers, it started to work in 1989. This was not the time of LHC. This was the time of another accelerator called LEP. So LEP stands for lepton electron positrons accelerator, and was not only accelerator, was also a collider. And in this accelerator collider, we studied these new particles we had discovered before, the W plus, W minus, and Z0. In year 2000, as the project with LHC was already, let's say, ready to go, to be built, we stopped the program of the LEP accelerator. We dismantled, we removed all the parts of the accelerator, the previous accelerator, and we started to fill with the new parts of the LHC, the tunnel. And we finished in 2008. And we started in 2008, in September of 2008, we started to circulate the beam. So summarizing, you have the beam injected in the LINAC, then it goes in the PS as a beam, and then it goes again in the SPS, and then finally 2 beams are sent, one in one direction, one in the opposite direction in the LHC. Last thing, and then I would like to check if Laza and Noemi are around, otherwise I will continue, is that the more you increase the radius of your ring, the more the energy increases. So it means that the energy, the maximum energy your beam or particle can get in the PS is less than the maximum energy you get in the SPS. For scientific, as we use this unit, the GeV, giga electron volts, we have a maximum of 25 GeV in the PS, 400 GeV for the primary beam in the SPS, and then now with the LHC, we can reach, let's say, 7 TeV in the CMS. Sorry, in the LHC is not exactly 7, is a little bit less, but okay, let's say roughly is 7. Zoltan, do you want to add something else on what I said as a general description?
I think that was completely fine. I'm just trying to find Laza.
Yes.
to put his picture alive.
Yeah.
If you could stop the sharing, it might help.
Yes.
But I will ask you to speak a little bit more.
Sorry. Just let me see. So stop share. I did stop share.
Okay, we don't see Laza still.
Yes, because I saw him at a certain point. He was entering the. So Laza, what is doing Laza? Now Laza is going through. He has to take an elevator. Now, how do we access underground? We have special doors. The first one is before the elevator we can use to go underground, and this door is a special door because you are checked for 3 things. Let's say basically, one is your weight. Is not because they want to know how much is your weight, but it is because you are not allowed to go through these doors with the material. So you cannot bring very heavy things, and this is why, let's say, the system is set in such a way that is detecting a human weight, let's say. Then you have another check, which is done with the infrared beams, which are checking, for example, if you enter with the backpack, okay, with some large objects, because also from these doors, you cannot bring any large material. And then the final thing is to recognize people. We have the biometric check. So we had to show our eyes We already registered in the at Cern our iris, and so we have this recognition. I don't know if any of you, maybe yes, a few, because we are many, saw the movie Angel and Demon, and maybe some of you can remember the first parts of Angel and Demon, where the person who has to steal the antimatter has to enter inside the lab, and so he's using such a kind of door to enter in a very, I would say, bad way for the person who is the victim. Okay, I don't want to spam too much if you didn't see this movie, but okay, is exactly using this door. You can ask where we can then bring inside the material. We have a special door where we put the material, and then once we have checked with these special doors for people, we open the other one for material, and we can recover the material we put before inside. And for very huge parts, we have cranes which are going down through shafts. I hope that Laza will be able to show us also these parts. So there are some holes, let's say, which are going directly down to bring material up and down. So you have the both. You have a material from the surface inside, or the other way around, if you had to check or to remove or to replace pieces of the detector during the stop, the technical stop, as we have now. I still don't see Laza, so I will continue. Maybe I don't know if Zoltan, I can share again something, or I will start to describe a little bit what we should expect to see. And
go ahead. We are working on this little technical issue.
Yeah. Okay. Sorry, there is a question, so maybe I can know how much of a concern are. Sorry, let me put, because okay, I had to put also. Now in the tunnel. Let's talk a little bit in the tunnel. Now the tunnel, as I said, there is the accelerator inside. So you should think think the accelerator as a long pipe, circular pipe, made of different parts, which are the main parts of the accelerator. We have parts to give energy to the particles. I didn't mention about the particles in the maybe I can share again. Zoltan will tell me if I have to stop the sharing. Sorry, let me share again. Is here. Okay, share. Okay, let me go back to the pictures. Okay, I said that at LINAC 2 we inject particles. Which kind of particles? We inject protons. Now, where we can find protons? You can find protons in a very easy way inside the simplest gas we have in nature. Okay, I can see now underground. So we say this, and maybe I can leave the floor to them because they are showing something interesting, I guess. So these particles, they are protons.
Okay.
Yes.
Can you hear me? Very well. Okay,
Yes,
it took a while. Sorry, Zoom is still new here. So
Laza.
Sorry about delays. Can you hear me clearly?
Yes, we can hear you, Laza. Can just I finish to say where we get protons, and then I will leave you the floor.
By all means, carry on. We need protons.
Okay, yes, just 1 minute. So these protons, what you do, you get hydrogen, and this is easy because hydrogen is in the atmosphere. And then from a bottle, of course, we have a bottle as an extinguisher, a fire extinguisher. We have this hydrogen. When we apply an electric field, and we can separate, we can split the proton and the electron, which is making the atom of the hydrogen, because this is the simplest one proton and one electron inside. So you can split them, and then you throw basically the electrons, you keep the protons, and then you inject the protons through the LINAC, okay? And here starts the travel of these particles, which are then, let's say, formed as a beam, and in particular, they are grouped in packets, okay? So you have packets of many billions of protons running inside the accelerator. So they go through the APS, and then they go through the SPS, and then finally they go through the LHC from two directions. And then when you have the bunch crossing, basically what you crash are the two packets together. But now I think the best thing is to give, yes, I was talking about this shaft. So maybe Laza, if you want to describe, because we were wondering how we can bring up and down the material. So Laza, the floor to you.
Okay, there are two shafts and two caverns in CMS. What you see here is a surface shaft where we can lower only objects up to 20 tons. When you work in an experiment of 14,000 tons, only 20 tons is really only. The bigger shaft that you will see later on can be used to transport things up to 80 tons. So to remind you, CMS stands for compact muon solenoid. And here you have a little mock-up that we use as an introduction for people who manage to make it this deep underground. And here we are going through the service part of the service cavern. The CMS stands for compact muon solenoid, meaning that solenoid is a very strong magnet of coil type. And what I want to show you is the place where we liquefy helium. Strong magnetic fields you can achieve only with superconducting magnets. And this is so-called cold box, where we compress the helium arriving from surface, transform into liquid, and then through these big pipes, send into the underground cavern, which is on the other side of the wall. As you can imagine, huge experiment like this requires lots of power, lots of cooling, and that is usually unwritten story of big experiments, because we are concentrating on super high precision of track reconstruction and quality of the data, but not how well the experiment works. So I'll show you briefly that the unsung heroes of the experiment, namely isolation transformers. We use about 5 megawatts of power. That is, these are devices that allow us to operate well. We have to cool everything that is installed underground. We have to have safe access to the tunnel of the accelerator that is completely separated from the rest of the experimental cavern. This is the room where we have pumps, turbines, and cooling circuits for the whole experiment. As you can see, there is heavy work going on because we are in a maintenance period. So you have, these are again, this is tiny part of the underground. I'm going now from the surface area. Oh yes, always a nice thing to show. These are copper conductors that send 18,000 amperes used to power our magnet when we operate. This is room temperature circuits, but you see how thick copper it is.
And
Thank you.
in the moment you go, I will add, if you allow me.
Go on.
Yes, to send. And these maybe if you have the chance to I don't know if from this site you can show us. Maybe if you go on the other side, these copper lines you were talking about, and then this is a way we can evacuate the energy in case something is going wrong with the magnet. Okay, I don't want to say it's just a comparison. Is as the ground system, the grounding system we have at home, so we can evacuate all the energy. So Laza was talking about the energy connected to 18,000 amperes inside, which are flowing inside the magnet. And so we can evacuate this huge amount of energy, and avoiding to destroy the magnet if something is going wrong, just evacuating this energy through these thick cables of coppers, and then they go out. There is other copper to absorb this energy, and then the rest is goes the ground, the real ground.
Yeah.
Yes.
That is on surface. Those so-called discharge resistors are on surface. They are, as everything else in at Cern, slightly over-designed, so they can work up to 600 degrees centigrade. And we never warmed them above 460, 70. During test discharges, we did not have an unwanted magnet discharge since the very, very early days of operation. And what I would like to show you here is an important part of the service cavern, namely so-called electronic racks of various subsystems. Triggering system, data acquisition system, neon systems. You see lots of cables, lots of fibers, cooling pipes. What is this all about? You have to control the experiment. You have to power it. You have to supervise low voltage, high voltage. You have to be able to turn it on and off. You have to increase or decrease the values. And all that requires remote control that we establish here. Another thing is that the data coming out of the experiment, you cannot fully use. Some of that, actually most of it, are known events. So you have to filter out only interesting part. And for that, we have so-called readout electronics that does two-step process of extraction of only interesting events. The first step is done here underground in custom-built electronics that reduces the frequency from about 40 megahertz of event collection down to about 100 kilohertz. Those elements that go to this level of triage go up on surface, where events get fully reconstructed, and then another level of triage is done, where we choose maybe a gigabyte or 3 of events per second, because our writing abilities are limited, like any other computing system. I'm going now.
Yes, you go
to
down.
approach.
I leave you to continue, huh? Yes.
Yeah, a little bit longer. Here is, like any other underground system, we are very worried about fires. And here you can see the system of fire detection, smoke detection. Nobody was ever heard of even thinking about smoking in underground. And here you can see a tiny section of cables connecting the experimental cavern and the surface cavern. There are thousands and thousands of kilometers of cables, and it was a titanesque job to all of them install, test, and verify that they are correctly plugged. Now, what you can see here is, oh yeah, interesting thing. When your experiment is half an hour, even for firemen from the medical surface, there are dozens of us trained rescuers. So if anything happens, there is always somebody to help you on the spot. We usually keep the experiment separated from from the LHC tunnel because the rules and the dangers are different. So this is one of the doors that connect the LHC world with the experimental world. As you can see, it's under alarm. Access is not allowed unless there is a very strong reason. And I'm now going through the chicane, a zigzag system that actually protects us from the neutrons coming out of the collisions. Here is the wall. This is 7 meters of heavily armed concrete between the experimental cavern and the service cavern. Now comes the joy of accessing the experimental cavern. So I have to badge. I have to enter the opening. It of course doesn't like when there are cables hanging around.
So I help you. Okay, as I described this door, you can show us. This door is the same, is another door, is exactly the ones I was describing. So now Laza is badging his dosimeter. He enters. Now you cannot see the feet of Laza, but he's standing up on a weight sensor, and you can see the black part is he was doing the biometric check. Maybe he can. Laza, can you show us maybe the bottom?
Okay.
Yes. Okay. Yes.
Okay.
Let's see Noemi.
Noemi will be the model this time.
Yes,
Okay.
and then she's
now turning around, reading the iris, being recognized or not. The system is very delicate. Yeah, recognized you today.
Yes. Today
okay.
you are lucky.
The system actually has multiple light rays. So if my cable crosses it imagines that there are 2 guys trying to simultaneously access the cavern, which is forbidden. So sometimes it's nervous and it takes a while to get through. And now we're entering into the center of CMS world. Welcome to CMS.
Yeah.
So this is the real thing. We are on the so-called visitors platform, and we are at the level of the beam pipe, the vacuum pipe through which we send the beam through is not at the moment in place because we are working, we are repairing things, upgrading things. And here you can see the central part of the experiment.
Can you show us, Laza, with your finger, the ring of the magnet and just indicating a few parts?
Well, the magnet is this big silvery thing. So the inner diameter of the magnet is 6 meters. And the yellow cage with the net that you see is actually a working platform that people are repairing or replacing electronics use to more easily access the electronics sitting there. So the big magnet is a thick silver cylinder. Inside are, of course, tracking devices, electromagnetic calorimeter, hadron collimator. On the outside, the red elements are the magnetic yoke for return of the magnetic field. And the silver objects are resistive plate chambers and drift tubes, so-called muon detectors. Why muon detectors? Muons actually give very nice signal. And the whole experiment was built around a very good capability of reconstructing muon tracks.
If you allow me, Laza, I would say that in any case, CMS is detecting very well also other particles, even if it was thought for muons. Do you agree with this? You do a very good physics also with other particles.
Well, let's say the early days, the must was, okay, we must have a brilliant muon detection. And then the next step was, but then we must have a brilliant electromagnetic calorimeter. And well, if we're already there, why don't we have an excellent tracking device? And then this little by little turned out that we have actually a very excellent detector. So what you see here is the end cap
calorimeters. The first conical part is actually electromagnetic calorimeter. The white disc at the beginning is pre-shower. The second blackish conical part and cylinder is a hadron calorimeter. Why is it useful? When you move the disc and it enters the barrel, we achieve hermeticity. So there are no dead areas of the experiment. All the particles created in the collisions in the center of the experiment are detected. None of them can escape through gaps. And yeah, but moving things in is not always easy. And what you can see here are the red support frames and orange discs at the bottom of the feet of the experiment. Orange discs are actually air pads. We move everything on air pads. This disc is about 1,500 tons, and moving it around is done regularly during the shutdown periods, almost not every day, but very often, because different systems need different accesses. And we have a team specialized in doing that cleanly and safely. I can assure you that even though the disc is 60 centimeters thick, the iron of the disc is 60 centimeters thick, it still wobbles a bit when you move it. So you have to be very, very careful. Being careful actually gives nice results, because the system of moving things around and locking the discs and the elements of the experiment in place, and there are altogether 13 of them, is so well done that when we reopen the experiment completely and put it back, the huge elements of a couple of thousand tons each are locked back into position with 100 micron precision. 100 micron on object that is 2,000 tons and 15 meter in diameter is pretty impressive.
Yes, in fact, if I can interrupt you, Laza, when you were going down, I was in fact talking about this, that this huge object is aligned with this kind of precision, and also when you close. So it's really impressive to think that you have an object which is high as a building of 5 floors and long as a building of 8 floors. So you can really manage to assembly and to close it with this kind of precision, which is on 1 million parts of a meter. So it's really impressive. And
there is a little secret here. You may be able to see a little piston sticking out here, and then an orange brace on the other end. Actually, the last 100 millimeters of the movement is not done on air pads and with the winches. It is done with hydraulic locking jacks that we have at every corner, so 12 per disc, 12 per ring, so that a very smooth simultaneous movement of hydraulic jacks allows that precision. And now we went 1 floor up. As you can see, cables all over. And I want to show you the big shaft through which we lower things in the experimental cavern. So this is top of the experiment.
if I can say, this is not is something you are not allowed to visit in person. So whatever
right.
Laza is showing you, it's really special. You cannot say, you cannot go there if you visit in person.
Yeah, I'm afraid that this place is not for visitors. You need training and you need safety clearances for that. So I'm afraid that the crane is a little bit in the way. So, but let me see if I can manage to do this. Yes, yes.
Yes, this is much
now
better,
you can
Laza.
see the roof.
Yes.
Now you can see the roof. Okay, Now, down.
Okay, in the meanwhile, you go down. Let me say that the diameter of the shaft, as Laza was showing you, is just really a little bit larger than the diameter of the slices of the detector. Because the
Actually,
detector...
I can show it. Actually, Sonia, I can show you this nicely. You see the edge of the gallery here, and you see the edge of the support structure. This is the clearance we had for lowering elements. This came down with the experiment. So this is the clearance we had.
Now, let me, emphasize this. It's really crazy if you think that you have these huge objects as a slice with a weight of about 2,000 tons. You had to lower for 100 meters. You had to avoid any kind of oscillation because you saw the clearance. This means that if you started an oscillation, really going left and right, you cannot stop, you destroy everything. This is why a huge crane from the Genoa harbor from Italy was installed all outside the building where we have the 0.5 here. And it took for the lightest parts of the experiment to be lowered down 8 hours about, while the central part, the part which has the magnet, took about 12 hours to be lowered. Laza, can you confirm this?
I can confirm. Well, there are millions of people who saw it. It was live transmission by BBC while it was happening.
Do you know if there are videos we can maybe address to our attendees? They can
actually, I don't know, but 12 hours of moving something at the speed of a couple of millimeters a second is like watching paint dry. So they will need lots of patience. No, I don't know the address, if there is, and I'm convinced there is. But
maybe if Google is not down, the Google site is not down, they can just find on the web the right link to see this video.
Okay, so now I'm on the floor. Now I'm on the floor of the experiment. This is the floor of the experiment. This is not the bottom of the shaft. Namely, the floor is at 97.7 meters, but we have about two floors more. Yeah, that's that. My assistant is showing where is 97.7. We have about 2 floors worth more of space underneath for passage of cables, cooling pipes. Some of the cables are hidden under these covers, and you may be able to see them coming out here and feeding the different subsystems. And again, this is a fortunate moment because we have lots of space between end cap and the barrel part of the detector, because that's what people working on the experiment needed. So you can see lots of elements, lots of chambers, lots of cables, lots of power. And now I'll show you a bit more of the cavern around. You see that there are central parts. There are 5 so-called wheels. Only central is fixed. Everything else can be moved around on air pads. Here is a bit of space to the next end cap. And Noemi will now demonstrate you that because of the strong magnetic field, we have a strong remnant field. So everything is slightly magnetized. Okay. It is not strong enough to, yes, that's better. It's not strong enough to ruin your wristwatch, but it is strong enough to be noticed. And now I'll show you access to the service shaft. So we have two caverns, two shafts, and this is passage towards the service shaft through which we came underground. And why is it open? Because we are working. This is shutdown period. The big tower of concrete you see in the back is moved on air pads before we start taking data. And this passage is completely closed with concrete and then sealed so that there is no air passing between experimental cavern and the service cavern. And what you can see here is so-called rotating shielding, excuse me, an element of the protection that keeps above all the magnets of the LHC protected from the particles created in collisions. And we are actually, this is part of the refurbishment of process. We want to repair it. There are some cracks to be filled. Oh, talking about potential problems, maybe you can see the big red nozzles. In fact, here, there, big red nozzles are one of our last lines of defense in case of fire. We have a firefighting system that can fill the entire cavern in about 10 minutes with foam that would stop any fire. The claim of the manufacturer is that humans can breathe, but fire cannot propagate. We tested the fire part. Humans, we didn't test yet. And yeah, more nozzles and more elements. Okay, we go through this. Okay, I think that.
If they don't want to.
Do you have questions, or shall we slowly start leaving the cavern?
What I can do in the meanwhile, if you don't have any, I don't know if you have you talked about the pads, no, the orange pads.
Yes.
Do you want to say something more? I don't know. Otherwise,
okay.
to show how big they are.
I'm at the moment. We got a question about the luminosity of the LHC. Of course, at the moment it is 0 because we are off.
Yes, of course.
But when we are running, I think we are at the design parameter. If I'm not completely wrong,
yes, you're completely right.
34.
You're completely right. We are at 210 to 34. We could go up to 5 during first 10-15 minutes of every fill when the beams are still strong. But the experiments cannot stand it. It's too much data. Another thing is that the magnets near the experiments see a little bit of debris coming of the experiments, and they warm up. So when you have too much of luminosity, you risk to warm up the triplets that do the final focusing before the experiments and quench them. So we artificially limit the luminosity to 210 to 34. Could be more, but not yet. That's the part of the upgrade to high luminosity LHC to have inner triplets that can stand more heat. Okay.
We also got a question.
Yes.
Just right.
Yes.
All the electronics in the collider room, I guess in the experimental hall, are not in danger of breaking with radiation.
Well, that is why we keep in the experimental hall only things that must be there. Everything that can be kept put a bit further away, we keep in the service hall. And things that are in the experimental hall are tested to be able to survive radiation. So yes, there is a bit of the radiation damage, but the design is such that it can work for a few years. Okay, just 2 seconds detour to air pads. We have 2 types. These are what you see here is big. It's about 1.20 meters in diameter, and they are for moving around really objects of a couple of thousand tons. they operate at 24 atmospheres. So the hoses you see feed the compressed air at 24 atmosphere, and it creates an air pad of a couple of millimeters that allows you to reasonably smoothly glide over the floor. By the way, the floor is covered with steel layer of a couple of centimeters thick because the pressurized air was damaging the pure concrete. So we had to deal with that more or less as soon as we started working with the experiment. Next question.
Okay. This is there is a question of safety. Maybe I don't know. You or Zoltan, you can answer. Is concerns the effectiveness of the fire system. When was tested? This was done this check.
So
I know there are regularly checks. No.
exactly. So there are two different things. One is the foam system, that is the last resort before we completely abandon the experiment. Laza can show the foam blowers. This system obviously cannot be tested in the cavern. This was tested in 2005 when the cavern was empty, so we know that this works. And also in 2014, we removed one and completely retested the system when we refurbished to the new one. Of course, this was not in the cavern. What concerns the other extinguishing systems, we regularly check them, as Sonia said. So every year we make a test, even with the water mist system, even with the carbon dioxide system, even with the nitrogen system. We often make a test, as also we do for the fire detection systems. So this is also very important.
Yes,
these are tests. Okay, sorry. Go, Laza. Go.
No, this is legal obligation that everything that can be tested is tested once a year. Every year we have to test every single emergency stop for power. So there are people walking around and hitting emergency stops. And of course, during that period, during that day, nobody is allowed on the experiment because you cannot rely on safety system that is being tested. So
I wanted to add also that not only the systems are tested, but also people, because we have a regular, not only because we have to pass the safety courses to be allowed to continue to work, but also we have sometimes evacuation tests organized. So people is really going down. At a certain point, there is the alarm. Of course, it's a simulation, but we should think it's not a simulation. We have to be able to find the right way to go out to reach the good points to interact with the fire brigades. So these are really regular checks. This is really important. Otherwise, you cannot really work in this kind of parts of the or locations. So Laza, I don't know if you want to say something about, because we are going out now, I would like to profit, if you agree, to show the picture of the detector, because we show the detector itself, which is the more important thing, but maybe to describe now, to have a picture, to summarize what you said, what you have shown in a picture, could be, if you have
and also,
nothing.
Sonia, we got a question on this directly.
Yeah.
So
yes, I was not reading the questions. Yes, okay. So maybe I can show this in the meanwhile, Laza, unless Laza has something special to show.
Well, nothing except to remind everybody that in undergrounds of LHC, the safest place is actually staircase and the elevator shaft. And that is why we have to do those evacuation exercises to make sure that we actually can fit everybody in safe space. But believe me, you become really best friends with your colleagues, queuing with you in a so narrow but still very safe space. Okay, we're going back to surface.
Okay, Thank you, Laza. So I will summarize a little bit what we said, what we saw. So as you see on the screen, we have this picture showing you the location of the LHC and the location CMS. As I said, is the farthest from the reception. Natale is just behind the globe. You see the SPS, which is higher with respect the LHC. And then, okay, I can go after. We have, sorry, we have other, why I cannot go more. Okay, yes, here we have the 4 detectors. You can see on the top right the CMS, and we have also Atlas, Alice, and LHCb. Let me make a comparison. CMS is called compact muon solenoid. The size is smaller compared with Atlas, as Atlas is much bigger. Consider that the length of this detector is 45 or 46 meters, which means a building of 15 floors, while the diameter is 27 meters, a building of 9 floors. CMS, as you saw, is smaller, so the length is about 25 meters and the diameter is 15 meters. I repeat, in floors, a building of 8 floors sleeping and a building on 5 floors standing up, the diameter. But if you compare the weight of the two, CMS has a total weight of 14,000 tons, while Atlas has exactly the half, more or less the half. So this is due to the technology or the assembly technology, the technology of each device. Basically, the main part of the weight of CMS is comes from the superconducting magnet, as you saw. And for this, the returning yoke, this red part, which is part of the also is let's say in the muon chambers, which makes us able to keep the magnetic field all around the detector. Okay, now this is not we cannot do 100%. We have a fringe magnetic field also. We can feel outside the experimental cavern, but this is really low, so we can we are able really to keep the magnetic field around the detector. Let me go again, as there is a picture. This was a plan, a planimetry, let's say, the planning of the what Laza did, but it's too technical, so we skip, and here we are. So you see the detector. This is a picture. So starting from the central part, you see this gray pipe. This is the beam pipe from LHC. And it is going through the center of the detector. So you get one beam coming from, if you follow my mouse, let's say from the right side to the top, and the other one coming from the top side on the left, and crashing in the middle of the detector. And then first you get the tracking system, with this green part, which is made of 2 technologies of detectors. Are silicon detectors, but one part is in pixel and the other is done in microstrips detectors. And then you get this yellow part here, which sorry, there is first there is the electromagnetic calorimeter, which is this other one, is also more or less the same color of the tracking system again, for to detect the light particle, let's say electrons, photons, positrons. And then you get the yellow part, which is the hadron calorimeter for protons, neutrons, and or hadronic part, so particle made of quarks. And then you have the magnet, everything is inside the magnet. And then you get the muon chambers and the return yoke. And I would say a peculiarity of CMS detector is that usually most of the experiences, they use the magnetic field, Laza is here, use the magnetic field only for detectors inside, while in CMS, the magnetic field to make measurements is also used outside. Maybe I have the other picture I can show you. And yes, Laza, do you want to comment with me as they are back again? Maybe I can move. Okay. So as you can see, let's start again from the center. Now you see from the left part of the left part of the slide, where my mouse here, you have the collision point, and then you start to see all the particles going through. This is a cross section of the detector, and you can recognize the tracking system, and then the electromagnetic calorimeter, and then you have the hadronic calorimeter, the magnet, which is this CM part, let's say, and then you have the muon chambers and the returning yoke. You see that there is an S as my name, Sonia. So why, Laza, do you want to say something about this?
Because charged particles curve in a magnetic field, and we have magnetic field in two different directions. Inside the magnet it's in one way, and outside the magnet and the yoke it's in the opposite direction. That's where there are two curvatures. But that two curvature system allows a really nice reconstruction of the magnet tracks. I'm sorry, muon tracks. What I actually love to remind people, you see, from the interaction point to the outer edge of the CMS, you have about 7.5 meters. However, the experiment itself is 22 meters long, which, when you think about it, they collide bunches of particles every 25 nanoseconds. Moving with the speed of light, secondaries cross 7.5 meters in those 25 nanoseconds, meaning that the products of one collision are still traveling through the experiment while the next collision takes place.
Yes.
And it's not particle by particle that collides, but bunches of particles. So we have usually 1.3 10 to the 11 protons per bunch, meaning that we work with so-called pileup of 50, 60 even. So you have 50, 60 simultaneous collisions, products going through a huge detector. And then while they're still going through, here comes another and another and another. So the joy of the people working on filtering out interesting events in real time, and the possibility to make a mistake. Just imagine one tiny fraction of the detector has a slight delay with respect to the rest of the experiment, and all of a sudden you start reconstructing part of the one collision, adding
and the part of the previous
the
one.
other, and either it's a Nobel Prize or maybe not a Nobel Prize.
If I can say something, you are reminding me, do you remember this time? Because, you know, physics is, as Laza is saying, is also a challenge, is also to fight with the mistakes, to be able to correct, to understand. Do you remember this time when some experiences announced that the neutrinos were going faster than the speed of the light in the vacuum? And this was a cable. So there was a measurements, and because of a cable which was a connector which was not working properly, they were getting a wrong measurements of the time. So the moment you were calculating the speed, it was higher than. So this was a huge it was a discovery, because we were going
no, it was not discovery. No, they were much more serious than
that.
But
These I know, but
it
would have been if it would have been right, you know, correct, it would have been a huge impact, because you were saying
exactly. But when I saw the presentation of the spokesperson of the Opera experiment, his conclusion was not the discovery of the superluminous neutrinos, but asking for help to find the problem.
Exactly.
I saw too, and you know, I'm Italian, so I had to protect that these were Italian scientists. No, you are correct. There were journalists, let's say, they were saying a little bit more, but the scientists that were just asking help because it was really strange to find this kind of result. But if it would have been right, it would have been a huge impact in physics, as you said. So we had to manage with this kind of possibilities.
Part of the job.
Let me just make a remark here, because this is a very important thing, and that's why we have Atlas and CMS on the
Yes,
LHC.
exactly.
And the Atlas and CMS are built completely differently by people who were, I wouldn't say that we didn't discuss with each other, but we tried to be as independent from each other as much as we can. The analysis teams really do not communicate with each other. And this is the guarantee that if we discover something, and if the other experiment see it, then this is a real discovery. If not, then we have to go back to the
Yes,
commenting desk.
Can
Actually, this was one of the questions that I wanted to promote here, but I already pushed it to the answered region. So what are the other experiments do at the LHC? So Atlas and CMS are very close friends to each other, even though they are completely different. The Alice is looking for the heavy ion interactions, even though the Atlas, both Atlas and CMS has its own heavy ion program. And the LHCb is completely different. They are looking for the CP symmetry breaking.
Okay, may I now
May I say
go
this is a scientific
to the
competition.
chat questions?
Yes.
What is the safe period for after the collision? Actually, remember, we work with collisions. So at the end of the fill, when the beams are dumped, we usually wait about 20 minutes before we allow people into the cavern. We usually don't allow people into the experimental hall unless there is a very good reason. But when we do, then the first people who go in are Noemi and a couple of other guys with radio protection devices to make sure that there is no activation of air, no activation of support structures in the area where the people making intervention are working. So they enter, they check the air, they check the passage, they check the rack where the electronics board has to be replaced. And only once they are done, yes, the device itself.
Yeah.
So once they are done, they actually can say, look, you have 2 minutes. After 2 minutes, you are not allowed to stay. You have to go back, and somebody else has to come and do the reconnection. Why? Because we have strict limits to allow those.
Yes, and I can, yes, okay, Zoltan, go.
It differs from point to point in CMS. So close to the beam pipe or close to the forward region, the radiation, the remaining radiation is higher than at the bulk, the barrel part of the experiment.
Luckily.
However, we all work, as Laza already said, we all work by very strict rules, and we before anybody would start to work in these short access periods, we always measure the place before, and we decide what can be done. So that is a BOMO that we always keep in mind: safety first.
At least from what I know is that we are, okay, of course, we are, Cern is in Switzerland and France. However, there are some rules from the countries, but Cern is even more strict on these rules, really to protect everybody, not to be in a dangerous situation.
By law, we have to satisfy all the laws of the host states. So France,
yes, but as I know, it's even
usually it's the more strict,
yes,
of the two. Mm-hmm. So European Union, Swiss laws. Sometimes for a while, Swiss laws were more strict than French, and then European Union, especially for in radiation protection area, tightened the rules so that things became really complicated. Actually, it costs us time.
Yes, I know, but in this way, you are confident that you can really work.
Yeah.
Let's say this is how to say, you pay one side, but okay, I don't want now to compare with the COVID situation, but this is maybe you feel better if you are you have strict and tightened rules, even if they are not how to say comfortable.
Well, look, it's not my feelings that count. It's the law that has to be followed.
Yes, okay.
So forget about feelings, just do it. No, processing of the
Yes,
data.
the data
Actually,
the collision.
there is, our trigger has two-step process. One is on the hardware level with field programmable gate arrays and custom built ASICs. We do the so-called level 1 triggering based on information in calorimeters and muon system. Why? Because there you have practically instantaneous information about how much energy went into which part of the experiment and how many muons went where. So that is the first level of triage that allows us to go from 40 million to 100,000 potential candidates. You have few microseconds for that. The time is defined by the depth of the buffer for the tracking system. Because if you think too long, the tracking system will simply run out of memory and won't be able to to provide the event that you eventually found interesting. Once the potential event candidate goes through the first level of decision, the fragments are sent through optical fibers, of course, to the surface to our online farm, where the event is fully reconstructed. So all the tracks inside the tracker, all the muons, all the energy in various parts, all the calorimeters. So we have a couple of megabytes of an event. Then it's compared with if I remember well, it's still 128 potential candidates that of events that we want to look for at a given moment.
Okay, what's a muon? Okay, muon is a fundamental particle. I don't think we have a standard model. Zoltan, do we have a standard model picture? No, we don't have. So there is a live question which is concerns what is a muon and why is important to detect them. So consider that what we know now, what we discover, okay, is that the standard model, which is the description of the particles, fundamental particles in nature. We should have on. We are trying to share a picture. They are made of 12 particles, 2 families, quark families, and the lepton family, and they are made of 6 particles each. And the muon is a part of this lepton family, is let's say a cousin of an electron, a little bit heavier as an electron. Now, why is important? Because the aim of LHC, and in particular, yes, you can see on the maybe we can see, so you can recognize in violet you have the family of the quarks, and in green you have the lepton family, and you can see the electron which is close to the electron and the muon. They are close together. As I said, is a little bit higher weight as the electron. Now, why is important to detect muon? Why CMS was really, how to say, trying to detect muons? Because we wanted to detect, to hunt the Higgs boson. Yes, come here. Yes, and so one of the most probable channels, let's say, way to detect the Higgs boson was to detect a group of 4 muons. Because the Higgs boson you cannot detect directly, but you can detect the particle. This boson is decaying, is transforming. And so for muons is one of the pictures you can find, you can look for inside the detector. And this is why it is one of the most probables. So this is why it was so important, and CMS really started to build the best detector they could do to detect muons.
And that we could pay.
But I can say that, okay, I insist that the detector is detecting also other particles very well.
Oh yeah.
Yeah, I have one more.
Yes.
One more remark on this. This is very important what Sonia said. But Sonia, if you could just share back the detection
yes
slide.
Yes. Okay, we go. Which is this kind, this nice S.
Exactly.
Yeah.
That's exactly this one. So
Yeah.
in the collision itself, enormously many particles are created. Many of them really, maybe a little bit, I wouldn't say too much for the trigger, but this is very, very high number. But as you might see, most of the particles, almost everybody, will be captured by the colorimetry system. Electrons and photons in the eCal, hadronic particles in the hadron colorimeter. Only one type of particle, well, actually, what we measure, can go through this system, and that's the muon. Therefore, the muon spectrometer data is very clear. And from this, it is very easy to make a trigger on muons. Laza will tell me or tell us that there are, of course, lots of other trigger opportunities or trigger possibilities, but this is the easiest to be explained.
And fastest.
Exactly.
Yes.
Okay. There are few
Maybe
more
we can
questions.
connect this.
One is about future. Future for LHC starts in a couple of years. The long shutdown 3, a large number of magnets will be replaced, and we will switch to high lumi LHC, that where the design luminosity will be 5×10⁻34 instead of 2×10⁻34. And given the current state of progress, it will be the beginning, and then they will ramp it up even more. Now, high lumi LHC is supposed to operate from 2026 to 2036, 2040-ish. And by then the next generation of accelerators, if we get approval and if we get funding and if we get this and that, may take place. What I understand from Cern management and European strategy in particle physics is that the idea is to start with the so-called future circular collider, colliding electron positrons in a ring of about 100 kilometers. Of course, this is all on the level of ideas and concepts. When and how it will go is going to be decided in the next 5 to 10 years. Problem is always
which is the usual even even a really short time with respect the time scale of these kind of projects.
Yeah. Well, think about it. First time I heard about LHC in 1984. Then it was presented to Cern as a project in the early 90s. CMS got incorporated in 1992. LHC's project got approved in 1996. Digging of the caverns could start only once LEP was closed in year 2000.
Yes.
So the first collisions 2008.
Yes, so this is the time scale of this kind of project because of the work. I wanted to say something about this. If you allow me to say, okay, for the Marcus question. So you are talking about a sinus. Now, let me say it's not a sinus. I don't know if you know the Lorentz force, but however, let's say like this, you need the 3 ingredients here. One ingredient is the magnetic field, and the other one is the velocity of the particle. Now, if you see this symbol I'm indicating, this cross here, and here you have a point, this means that you have 2 vectors. So one is entering the screen and the other one is going out of the screen. Now, the fact that you have, this is the magnetic field which the particle, the muons, feels in the first part of the detector inside the magnet, and the magnetic field felt by the muons outside. The fact that the magnetic field is reversing one side or the other means that the curvature is the opposite. Now, I cannot explain much better than this. Okay, I can use the hands, but you need really to go to the Lorentz force if you want to go deeper in this. It's really easy. It's just an inversion, the opposite detector, which makes that you have the curvature in one sense and on the other side, which is inside the magnet and outside the magnet. So it's not a sinus, it's just
so as the
opposite
magnetic,
curvature.
yeah. So as the magnetic field reconnects, it creates an opposite magnetic field outside the magnet than inside. And as Sonia said, this is not sinus. This is two toroids, or two well, circles, if you watch it in the plane, connected with I think a line inside the magnet. So that's why it is. The other question, the Feynman graph. It would be too much Feynman graphs, because we are looking not only for one physics process, but approximately 200 at the same time. We record all the data that are interesting. That's the trigger, what tells it. And then we have a bag of, well, I always used to somehow explain it with a rubbish bag, that we have lots of things in it, and we try to figure out, poke into it and try to find the events that we are looking for. So it is not just one Feynman graph, not just one physics process we are looking for.
If I can put some a comment only for people who are not aware what a Feynman graph is, imagine maybe, I don't know, you saw equations, you saw formulas, you saw some mathematics. Okay, the Feynman graph is also a way to see in a picture this kind. Okay, it's not only this, of course, this is really a rough way to describe them, but in a picture you can really put the equations describing the process, and this is a graphic way to describe what it's really happening in the physics. But as Zoltan said, there are many, but it's really nice when you understand them. This I can say. Okay, Laza.
The next one is the heating of the magnets. Our magnet, experimental magnet, will not heat because the density of energy is not that high. What will heat are inner triplets, the final focusing magnets of the accelerator. They are the critical ones. Actually, the run that we hope to start, the so-called run 3, we hope to start in 2022. They have to be very careful so that the radiation damage does not destroy them, the existing magnets before their time. So they have to be careful. But that's why there is transition to high Lumi LHC. For us, the problem is so-called pileup. At 10 to 34, we have 50, 60 simultaneous collisions. With 5 times more luminosity, we will have to work with at least 150 simultaneous collisions. We'll have to improve tracking. Second, our innermost detectors will suffer more from radiation. So pixel detectors will probably have to be exchanged more often. Second, we are building a whole new layer of detectors, very thin detectors, so-called timing layer in barrel and end cap, that are supposed to help us to distinguish where in that small region of collisions the secondaries are coming from. So we are upgrading our detector to work faster, to be more radiation resistant, and to have so-called better granularity, so that you're able to reconstruct the event with very, very, very good precision, even when there are way too many simultaneous collisions.
If I can rephrase, I would say that it is as if you go to have, I don't know, a radiography, a medical investigation, and you do not see clearly what is going in the picture. So you need really to see clear. And so this is what the granularity can make you able to see much better, much precise things, because you can really investigate better the location or whatever is, or in energy. There are many parameters. Okay.
Okay, the next question is powering of the experiment, and actually experiments are small fry when compared with the accelerator. Accelerator is
is much bigger consumer of energy, but no, we don't expect troubles. Well, nuclear power plant in Myhre works most of the year for us. It's only in deep winter that Cern switches from French power to Swiss power.
Which is not very bad.
Which is very expensive.
But then we do not accelerate them.
That's right.
We just keep
Yes.
the lights on.
I think Erwin was to say something. Yes.
Yeah.
Because we could continue, Erwin. You have understood.
Yeah, exactly. We already discussed with him.
I think indeed there are what you're saying is interesting, and there are people who have still questions. But I think we can go on still for very long, and we will not be able to exhaust all the questions. So I'm just conscious of the time, and I think there is a lot of information which is available also on the Indico page in documents which are available for those of you who want to know more about it. And what we can propose as well is, if you still have questions which you would like to ask, you can either send them to me, or I don't know if there is another address where people can send their questions to.
I think it would be good if you would collect them and then.
Okay, I'll collect them. So people have my name because they all have received messages from me, and they will receive more messages from me as soon as the registration is available on Indico. I will send the mail around, and there is also a very little survey which we would like you to complete. It really takes only 1 minute, and it's also available on the Indico page, and I will send you a link to that as well. So I would really like to thank all the people in CMS who have been working to make this visit possible. It was really interesting to see, and as you can read also in the chat, people are really happy to have been able to go underground together with you and see the detector. Many thanks to the whole team, and I wish you a very good end of the year. On Friday, Cern will close for 2 weeks, and I think we have all had a very difficult year with COVID, and lots of works to be done suddenly in many different ways. So I think we will need this period to charge our batteries and come back in 2021 for tackling the new challenges with full energy. Thank you.
Let me thank you. I think we should thank you also, you who organized for the people this event. And if I can talk maybe in name also the team, we hope that also our enthusiasm was really going through the screen, and the fact that we are all here chatting and continuing for forever is because really, okay, maybe there are also young people who wants to start this kind of career, not only those who have chosen this kind of career, maybe they could be inspired. I think this is also a good way to inspire them. So really thank you to organize this kind of events.
Thank you, and
Thanks.
bye now.
Bye.
Bye. Happy New Year.
Happy New Year.
Happy New Year to everyone.
Ciao.
Bye.